Hello, welcome to next session. In this session, we will solve remaining questions of production and industrial engineering date to 2019. Okay, so question number 46 is during a storm, the wind speed is 90 kilometer per hour. In a high-rise building, there is a window of size 1.2 meter and 1.8 meter facing the storm on an upper floor. Neglect the ground effect on the wind speed and considering the density of air, raw air as 1.2 kilogram per meter cube, the force in Newton acting on the window due to storm is okay. So when the storm striking the window, it will come to rest. Okay. So Bernoulli's equation is applicable to that. Okay. This is the condition when the air is in an atmosphere, and this is the condition when the air strikes the window. Okay. So initially the velocity is v square by 2g, and this is p where force is where 8 on 800 8.0 Newton. Okay. Okay. Next, the heat transfer efficiency in arc welding of a plate using a current of 250 ampere and 20 volt is 90%. The heat required to melt the material is 10 joule per mm cube. If the cross section area of the weld joint is 30 mm square and travel speed is at 5 mm per second, the melting efficiency is dash round of to decimal. So the heat input is your voltage and your current and efficiency. Okay, so that is voltage your 20 and current is your 250 and efficiency is your 100. So this is heat input. And but the heat required is your 30 mm. Heat required is 10 joule per mm cube. Okay, so the area is your 30 and this is your 5. Okay, so this is your so the heat required is your 10 into 30 into 5. Okay, so this is your heat required is 1500 joule per second. Okay, so the efficiency is your heat required by heat input. Okay, so that is 33%. Because heat this is in joule per mm cube and joule and 30 into velocity will be the mm cube per second. So this is the heat required per second and this is the heat input. Okay. So answer is 33. Next, a sand casting process has a mold constant of 2 seconds per mm square and solidification exponent of 2. The solidification time is to be doubled for a given unit volume of the material. The corresponding reduction in cast surface area in percentage is according to Cornick rule. We have solidification time directly proportional to volume by area with exponent constant and this is a constant. Okay. B is mold constant that is your 2 and explanation solidification exponent is your 2 so n is your 2. Okay. So this relationship is your T 2 B by A 2. Okay. So when So when volume is V and area is your A1, okay. So the time of solidification is your this. Okay. In the second case, the solidification time will be double. Second case, the volume is constant and solidification is get double. So T2 is your double of T1. Okay. So uh, B B is same constant and N is same constant. And B is same. Suppose area is changed. The area is your A2. So now from one end from this and this T1 and T2 we get this. So T1 by T2 is equal to A2 by A1. Okay. Putting the value of N is 2. Okay, we get and putting the value of T1 by T2 that is 1 by 2. Okay, so we get A2 by A1. A2 by A1 is 0.7071. Okay. And the change in area is your A1 minus A2 by A1. So that can be adding, sorry, subtracting 1 from here. We can put 29.29% or 20. Okay. Next, during a turning operation of a specific work material having shear strength of 220 MPa under orthogonal cutting conditions, the process parameters are, so this is speed, depth of cut, rectangle, and feed is your 0.2 mm, depth of cut is 1 mm, back angle is your minus 1 mm. Okay. So these are the parameters given. Given chip thickness ratio as zero point 0.5, the friction angle 42.9 and shear angle 25.4, the feed force in Newton is, okay, dash dash dash. Assume the principal cutting edge angle is 30 degrees. Okay. Given that the shear stress is your 220 MPa. Okay. And width of cut is 1 mm. Okay. Depth of cut is 1 mm. Thickness is your feed per evolution. So that is feed per evolution. 0.2. Okay. Shear angle is 25.4. Okay. So now the from the shear stress given, we can find out shear stress. Okay. So shear stress is your width of cut or depth of cut, okay, into T1 by sine phi. Okay. So this is the area for the shear stress, and this is shear stress. So this is the shear force. So shear force is your 102.5796. Okay. Now what we have to find out? We have to find out the feed force. Okay. So the feed force, to find out feed force, we will calculate first the thrust force. Okay. Okay. We will calculate first the thrust force by using Merton second. So uh, this is the resultant. Okay. And this is shear force. This is normal force. This is cutting force. This is thrust force. This is friction force, and this is normal force. Okay. Okay. So this is your angle alpha, back angle. This is 90. This is lambda. This is 90 minus z lambda. Section angle. This is 90 minus lambda. Okay, and this will be lambda minus alpha. This is your shear angle. Okay, so we have all things, and this is the good Merton circle. Okay, now the Merton circle is from the Merton circle your FT. This is FT. Okay, FT is your FS FS. Oh yeah, FS divided by cos this angle, that is lambda minus alpha plus cos phi, okay, into sine of this angle, okay, lambda minus alpha. Okay. Now we have lambda friction angle as 42.9 and that angle as minus 5 degrees. These are given, and Fs as 102.5796. Okay. So we can calculate your Ft. Okay. So after calculating FT, so FT is your 264.86. We can also calculate speed force. Speed force is nothing but FT into cos of principal angle. Principal angle is given as 30 degrees. So this is your speed force. That is 290, 229. So this relationship we have to remember. This can be remembered by using virtual circle, and this we have to remember because this is the shear area. This is just okay. Next, a a CO2 laser in continuous mode is used for drilling a plate. The process parameters and their values are laser power intensity, laser power intensity is equal to 1 into 10 power 8 watt per mm square. Vaporization energy 5 into 10 power 6 joule per mm cube. Efficiency of the process 15%. Laser spot diameter 200 micrometer. The drilled depth in mm after 2 seconds is okay. Given that the laser power intensity is your this okay. So the this is in watt per mm square. So the energy emitted by the laser is the intensity into area. So these are diameter okay. And as the efficiency of process is quite sorry, 15%. Okay, so the energy that is the energy given by the laser, and that energy transferred to sport will be what to the efficiency. Okay, so and what the laser will do that laser will vaporize the material and then it melt it. Okay, as the vaporization energy is given as 5 to the power 6. Okay, so now. Their the evaporation energy is given per unit volume. So let D be the depth, or sorry, T be the depth uh, up to which the evaporation of the material takes place. Then this is the volume of the material. This is the evaporation energy. So the uh, total total evaporation energy is this. Okay, in joule is this, and this is the in joule. Okay, and this is your energy available. Okay, so this is energy available, and this is energy required. Equating these two, we will get equating these two, we get P is equal to 6. So in 2 seconds, okay, in 2 seconds. So this is the energy available in 1 second. So in 2 seconds, multiplied by two or divided by two. Okay, we get P is equal to 6. The laser will make or drill the hole by vaporizing the material. So the power available by laser will cause vaporization of the sport, and it will go on penetrating with the time. So after 2 seconds, will penetrate by an amount P is equal to 6 seconds. Okay. Next, a process which is a state of statistical control with plus minus 3 sigma has an estimate of standard deviation sigma 2 mm. The specification limit for corresponding product are 120 plus minus 8 mm. The process mean shifts from 118 mm to 122 mm with no change in process standard deviation. The difference in the process capability index is here the standard deviation is 2 mm. Okay, so the upper limit is 120 plus 8 and lower limit is 120 minus 8, 112, 112. Okay, and the mean is here, and the mean, and initially the mean is here 118 mm. Okay, so the CPU is given by upper limit minus mean divided by 3 into sigma. Okay, so this is your CPU, and CPL is given by upper lower limit, sorry, mean minus lower limit divided by 3 sigma. This is your 1. Okay, your CPU and CPL. Okay, and the process capability index is minimum of these two. So this is process capability index is just 1. Okay, now the CP when the mean is changed from 118 to 112, So the CPU will be your one. Okay, following the same procedure, just replacing 118 by 11122. Okay, and your CPL will be here 1.667. So minimum will is 1. Okay, so there is no change in process capability index because here the process capability index is 1. Here also the process capability index is 1. So answer is just 0. Yes. Next, a monitoring system has 7 components. The reliability of each is shown in figure. The system reliability round off to two decimal place. Okay. R1, this is R1, R2 and R3 are in series, and R4 is in R4 and R5, R6 are in parallel. Okay. This whole system is in series. So by using series and parallel combination, we will find out the total system is. Okay. For series, the Rij is a multiple of two reliabilities. Okay. Now these two are in series. Okay. So these two can be replaced, and these are in series. So these can be replaced. Okay. So R1 is your 0.5. Okay. Okay. So here it will be 0.35. 7 to 5.35. Here R5 will be 0.6. Okay. And by using that formula, we can 1 minus 0.35, 1 minus 0.6, 1 minus this. Okay. So this will be 0.2, 0.87. Okay, the R is 0.27. Now we get again in series. Okay, so then these will be multiplied again. This will be 0.174. Okay, next, a part network consists of 5 activities A to E. The time estimates of these activities follow beta distribution. The predecessor and successor ES relationship between the nodes and the time estimate is given below. So these are the activities A, B, C, D, E, and F, depicted by 1, 2, 2, 3, 2, 4, 3, 5, and 4, 5. And optimistic timer 2, 4, 5, 2, and 4. And most likely time is 4, 5, 8, 5, 6, and pessimistic time is 6, 12, 11, 8, and 14. Okay. Now we have to consider various other critical paths. So first of all, we have to find out the critical path. Okay. So, so to find out the critical path, then we have to find out the this is your T naught by 6 here. Okay, so this is your optimistic time. So this is your variable. Okay. Now draw the project number. So this is your 1 2. 1 2 is your 2. 1 2. 1 2 is your 4. Okay. And next 2 3. 2 3 is your 2 3 is having 6. Okay. So this is 2 3. Okay. This is after 1 2. So it is 2 3. Okay. Now 2 4. 2 4 is again given. Okay, now again 3 5 is given and 4 5 is given. So 3 5 is your 5 and this is your 7. So this is 4 6. This is project division is 4 6 and 5. Here from this 6 plus 4 10 10 plus 5. So they get 5 in weight. Say 6 plus 4 plus 5 10 plus 5 15 away. Okay, this is 15. So this is your 1 2. Sorry, this is 15 and this is 8 plus 4 plus 7. This is year 19, so this is critical path. So variance of the critical path is summation of the variance. Okay, so this is your answer. Next question. The sales of the data of the product for 5 years are year 2014, 2015, 2016, 2017, 2018. Sales 280, 268, 259, 270 and 287. Assume the forecast for the year 2014 as 260 units using the exponential smoothing method and with exponential smoothing constant and alpha as 0.5. The sale forecast for the year 219 is okay. So according to the exponential smoothing method, the formula is ft1 ft alpha yt minus ft. Okay, where ft1 is the demand for next year. Okay, forecast for next year. Alpha is smoothing constant and ft is uh, forecast for present year, and yt is your uh, actual sale of past of that year. Okay, so this is forecast. Okay, so from this we can get the forecast of by putting this yt is equal to 280 and ft is equal to 60 and ft is equal to 60. We get the forecast for next year. Similarly, using for uh, formula for next year. Okay, now the ft will be your 270 and yt will be your 268. Okay, and again the ft will be your 270 and likewise for for year 270, 2017 and for 2018 and for 2019 we get answer as 255 or 275. Okay, this is the answer. Next, the layout for an AGV system is shown in figure. The loading time is 0.5 minutes and unloading time is also 0.5 minutes. All the distances are in meters. So this is your AGV system. Here it has to unload. Here it has to load. This distance is 50 and this distance is your 55. Okay. So this distance is 20, this distance is 40. Okay. So what we have to do? Considering a vehicle velocity of 50 meters per minute, availability of 0.95, the traffic vector of 0.9, number of vehicles required to satisfy a demand of 50 delivery hour is okay, delivery per hour is so considering one vehicle only. Okay, so so first of all consider only one vehicle. So the vehicle has to travel 55 this, 55 this, 40 this, 40 this. The total distance will be 55 into 2 plus 40 into 2. Okay, so that is 190 meters. Okay, so the average, and the average velocity of the vehicle is your average velocity is 50 meter per minute. Okay, so this is so the time during traveling is the 3.8 minutes. This is distance. This is time. This is velocity. So time is 3.8 minutes. Okay, and traffic vector is point 0.9 and availability is 0.95. Okay, so now the time will be more because of traffic and availability will be if we divide it by traffic vector 0.9 and availability by 0.95, you will get time as 4.4 minutes, 4 minutes. Okay. Now there is also loading and unloading, and in loading and unloading both unloading and loading, 0.5 minutes takes place. Okay. So the total time during this revolution or during this circuit will be 5.444 minutes. Okay. Okay. So now number of in one repetition, it is taking 55.4 per minute. So one truck can make 11 repetition in 1 hour. Okay, so 60 divided by 5.44. Okay, it can make 11 repetitions. Okay, now so one truck can deliver 11. Okay, so for 50 delivery, We will need 425 or 4.55 or answer is 425. Okay. Thank you very much.